right. Day 3. Trying to code this from memory. Again, starting with the AutoGrad, and I gotta turn my suggestions off here. Let's do it for an hour. We need data, we need children, we need local grads. Equal the data, self.grad random initialized to 0, self.children, self.local grads. Okay. We need addition, other, equal to other if it's already a value instance, else we need to make it a value instance, and we need to return the actual addition. So self.data plus that data, and the children will be self and other. And the local grad is going to be 1 and 1. It's going to be virtually the same for the multiplication. Except, obviously, we multiply, and then the grads will be different. Their data, self.data. Okay. Eventually, maybe I will write in these extra functions, but I think it's a waste of time when I clearly know how these ones work. So let's do backwards self. We gotta fill out the topology, and then let's build it. Node visited. If node is not visited, we need to add it. Visited.add node, and then we need to traverse the child in node.children. Build topo child and visited. And then once we've gone all the way down, we do topo.add. I'm gonna get my AirPods. Okay. Hopefully this blocks out the fan in the background. I don't think so. I'm checking my audio right now. I wonder if there's a filter. Maybe a noise gate. Let's try it. Oh, I think that worked. All right, now we actually need to build it out. Man, how many times am I gonna build topo self visited? All right. Self.grad is equal to 1. For node members typo for child, local grad, and zip node children, node local grads. We're going to update that child's grad, and it is a product of the parents gradient. So we've got node dot grad times local grad. So node.grad is going to be, so let's say I want, the error with respect to some child. That is going to be the error with respect to the parent times the error of the parent with respect to the child, right? And the parent with respect to the child is the local grad, and the error with respect to the parent is node.grad. So that's all that this is doing. And then we have to add, the child might exist in many possible routes to the root, so that's why we have to add up all those possible roots. Okay, good. Done. It's raining out, gorgeous. You go 5, 2. Okay. I don't know why I didn't even end up using C. Whatever. Works. Good. Done. Next. Actually, I want to do dot product first. Dot XY. And yeah, so the reason that this doesn't work, or it won't work, I discovered is because I didn't define a recursive addition. Our add is going to be actually, let me just add these in right now. I don't have to worry about it. Yeah. So I guess another one that I could do, so all of these up to ReLU, actually, I think from now on I should try to implement myself. And these other ones, recursive addition, true division. So all of these just inherit from these other operations. So that's why they don't have to be defined. Yeah, and these don't require an other. So, winner, XA. softmax. Yeah, I'm still going to skip RMS norm for now. So let's just do the attention block now, where we need query singular, keys, values, and DK. So it turns out, since the matrix multiplication is Q times the transpose of K, all those columns get obviously transported into rows. And so you can end up just doing a straight up linear with, hold on, it's QKT, which is the same as, basically, when I'm doing QKT, right, I'm taking a row of Q and I'm multiplying it by a column of K transpose. But that column of K transpose is actually a row of K. So it ends up being the same as if I just did K, a row of K dotted with Q, which is exactly what I'm going to do here. Its attention is actually going to be, oh yeah, and it's not sum, right? I think I made this mistake last time. It's this. Okay. It's going to be linear of query and keys. And then I need to DK, scale it down, right? For the, actually I can just do X, whatever. Scale it down, and then could even do it again and just do softmax, right? And then I do the same thing with the values. Oops. And really, I think that's it. Okay. All right. Now we initialize our weight matrices. So let's do our vocab, sorted set, join docs. Beginning of sequence token will be length vocab. All right, vocab size. Vocab size is length vocab plus 1. Our block size is going to be max for D docs. Great. So our n embedding is going to be 16. Yeah. Our dk is going to be 4, and our dv is also going to be 4. In fact, let me see what I can get away with here without even doing these. All right. So embedding matrices. Let me also define matrix lambda. Value. It's going to be random Gauss, not gamma variate. 0, I'm going to do 1, 4, and range C. How many columns we want? And 4, and range R. Great. Okay, so our state dict there. State dicts will be token, will be matrix. So the number of tokens we're going to have is our vocab size. And then our out is going to be n embedding, or W. The number of position embeddings we're going to have is going to be our block size. Okay. Now we need our attention matrices. So state dict, oops, W3, going to be matrix, and embed, and embed. It's going to be the same. The keys and values. Keys, values. Out. But so far, don't know. Oh yeah, W out is if we're doing multi-head attention, but we're not doing multi-head attention yet. We're still going to just do a single head attention. Finally, let's do an MLP matrix. Fuck it, we can do 2 today. P1. Remember, the row space is what's going to determine where we're projecting up to. So we'll project up to 4 like he does. And then we'll project back down. Great. And then finally, we need the last projection matrix. So state, I don't know what to call it. And this needs to go back down into the token space. So it's going to be vocab size and embed. All right. I think we are good to go. Let's try this. Nice. Now we need our GPT function. So GPT is going to take in a token ID. It's going to take in a position ID. It's going to take in our keys and our values. Okay. First, we need to get our query singular, and that's going to be a linear with, well, first of all, x token is going to be, sorry, shit, statex, w token ID, x position, position ID, and then our actual x is going to be the sum of these. Okay, now x, and then key, values. All right, keys dot, this is just going to be value. Key values dot append value. Great. Okay, and now we do attention. Block going to be attention query keys values dk 4. Actually, we have one head, so it should just be 1. I don't know, figure it out. All right, we don't have out matrix. Now we just go straight to the MLP. So MLP block. X is, I think, he would do some RMS norm prep, but again, skipping that for simplicity, even though it's already simple. All right, linear. So when this comes back, okay. Finally, to vocab space.
Yeah, technically there would be Rayleighs here, right? And whatever. Sure. All right. Super simple GPT block, right? Okay. Now, let's define our grad descent. We just need params, and we'll set a learning rate. So that seemed to work well yesterday. For P in params, P.grad. Oh, sorry, fuck. P.data. I was like, what the hell? P.grad times learning rate. And then set P.grad equals to 0. That's it. Now let's train. All right, now we get the logits from GPT. And we get our keys and our values. And then we do our prompts. Softmax the logits. And then our loss, this step, is supposed to be a negative log. Of the correct one, right? Yeah. Because remember, cross entropy is like it's y log y minus or plus 1 minus y log 1 minus y. Right? Something like that. Okay. Losses. Out of 10. Loss t. Rate. Loss is going to be some losses over n. Then we do loss.background. backward. Calculate those gradients. Big params. And that's it. All right, so we've actually defined our matrices. We defined GPT, we defined gradient descent. Let's see if this runs. Holy shit, first try. And then that was only one iteration, so obviously it hasn't learned anything. Let me just see what the loss.data is. Yep, that's about right. And then let's sample. So how are we going to sample? So to sample, sorry, I'm literally, my head is completely empty right now. I wasn't even thinking of anything. The sample, what do we need to do? We need to start with, first of all, we need to build up the sample auto-regressively. So let me try to fill this in. We're also going to have keys values empty, right? I mean, it's going to be the same, right? We need to call GPT with the token ID and the position ID, keys values. We need to get the probs. We need to actually sample something. Samples, I should say. Random dot choices. Wait, what's wrong with random dot choice? How's that different? Maybe I don't get to specify the weights. Yeah, I don't think so. Okay. So we're doing random dot choices from vocab. And our weights are going to be p.data for p in props. Okay. If sample equal to BOS, oops. Break, else token ID, is equal to sample. And samples dot append vocab token ID. Right? Right, because vocab does not include the BOS. Ah, you know what? Okay. Oh my god. Yeah. I'm remembering now. This is what you want to do. Vocab size, right? And then a sample is equal to, yeah, break token ID with a sample. Otherwise, you can do this. Nice. Beautiful. All right, so that's like 36 minutes. Let's actually train the whole thing now and see what we get. Train on the whole freaking deaking document. We are not learning at all. Why are we not learning? So let me make sure we're going through. No way the learning rate is too. Maybe it's too high. It's not going anywhere. It's not even budging. What the hell? All right, maybe I do need to implement Atom. Well, first of all, let me make sure it can overfit at least one name. Yeah, okay. It's starting to learn this name, at least. Slowly. Yesterday it was learning it much faster. There we go. Oh, that was weird. Big jump up in the loss there. All right, I'm going to stop it because clearly it's. Oh, there we go. All right, yeah. Learn to overfit. That's good. Works. All right. So now, um, guess we could do the RMS norm. Wow, just Armis Norm seemed to help. A little bit, I guess. My learning rate's maybe a little bit too high. All right, well, this is going. I'm going to make some more coffee. Breakfast. Yeah, loss didn't really go anywhere. Let's just try. All right, and then we'll try to do Atom. I actually don't know how to optimize it. I would do this. Okay, gradients. And we do the first moment vector. All right. Okay, one. Okay, two. Oh, well, this is annoying. This function is getting out of hand. Jesus Christ. All right. How do we do with this loss? I didn't really get anywhere. I guess we had to take a. Ooh, and I got to return. Oh, these depend on. And that's super annoying. There's not really a way to. Ah, damn. I just have to have this in the training loop, right? All right. First time looking at the. This doesn't even count because it's just for fucking Adam. But how does he do that? Yeah, son of a bitch. Okay. What's he keep? Is he just keeping this in a list? Yeah. Okay. We will do the same thing. MTVT. Oh, but they don't use the bias corrected. Division by 0. Beta 1 to the 0. Oh, is 1. Oh, I don't. Is he actually? I don't know if that is. Is he actually raising it to the power? Let's see what he's doing. Yeah. All right, but he adds 1. Okay. And me. All right, so this has been a good hour. Got closer today. So really the only thing I'm missing, well, I guess I should check my work here. So I added the RMS norms, but let me make sure I put them in the right places. Oh, I'm also not doing the skip connections. But yeah, so I'm doing the RMS norms in the right spot. I don't understand why he does it twice. An RMS norm here. I guess just the first time you go through the layer, it won't affect anything. All right, surely there's a more readable way to do this as well. And I think I know how I can do that. Yeah, he's storing all the keys in like a single. Okay, I guess that's fine. Hmm. He's picking off the columns. Yeah. Hold on, but keys is only two-dimensional. I think instead of trying to do this, I should just move on to my tensor implementation. Right? I mean, why would I force myself to do it? Yeah. I think I've already done it. Okay. It's for a different day. Lose my Sam. An alien today. Here we go. Frank is one of the 4 criminals in column B. An odd number of innocents below Bobby. Well, there's only going to be 1 innocent. Below Bobby, neighbor Pam. Exactly one of us 3 mechanics has an innocent directly below them. So it's already Amy. So that means that Pam has exactly 3 innocent neighbors. 1 will be here, 2, 3. There's an equal number of innocents in columns B and C. There's only 1 innocent in B, there'll only be 1 in C. Exactly 1 innocent in column C is neighboring Frank. So the 1 innocent is going to be there, which means these 2 will be criminals. There are exactly 2 innocents below David. Zed is one of Salil's 4 innocent neighbors. Salil's 4 innocent. Okay, there are exactly 2 innocents below David. All right, so here we go. Zed is one of Salil's 4 innocent neighbors. What do you know? 1 will come here. There'll be 2 here. So that's 1, 2. And then it can't be 3, 4. Why? Because there's exactly 2. It can't be 3, 4. So it's got to be 3 here, and then the other one has to be Martin. There's many innocent guards as there are us innocent sleuths. So far, there are 2 guards, 2 innocent guards, and 2 innocent sleuths. So then is that saying both of these have to be criminal? I think so. Here, 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 here. Innocent, innocent. What's wrong with that? Oh, wait, what? Two innocent sleuths, 2 innocent guards. Oh, because they could both be innocent or both be criminal, I suppose. Okay. Both be innocent or both be criminal. I suppose. Okay. If they're both criminal, then it's Ruth. If they're both innocent, then Ruth is. All right, so there's an odd number of innocents neighboring Gia. 1, 2, 3. They're exactly 2 below David, right? A number of criminals neighboring Vicky. I already know one of them is going to be a criminal. One of these will be a criminal. The other will be innocent. So I think that means only 1 mech has exactly 5 criminal neighbors. 1, 2, 3, 4, 5. There are 12 criminals in total. Oh my god. 3, 5, 8, 11, 12. Ugh. Only 50%. Yikes. Okay, let's do the connections. Mason jar, cookie jar, tip jar, bell jar. Is that a thing? Bell jar is a thing, right? Oh, none of that was correct. Style way. Round up, ring up, way up. The fuck? How is it not jars? Mason jar, cookie jar, tip jar, pitcher. All right, this is just pissing me off. Let's do the MIDI. Oh, I'm zooming in so much. Bills and coins. Base times height. Average billing. Snack aisle brand. Oreo. Got minis. Brew. Philly. Goes up, rises. Big giveaway. Tag. Alright. Things set. Hazmat. Cash. Ritz. Organ. Hot chili. Anchor. Site. Round. Something mancha. I gotcha. Catch-alls. Site? What? Can travel it. Oh, light. All right, what the hell's going on here? Bookmark cache. This is like a way of like putting it off till later. Right, I'm not getting it. Suffering from Grand's back splitting twist. So Grand's back splitting yoga twist. Grand's back is an N. Splits yoga twist. Agony. Animal taxa domestic. Oh. This is the shit that. So the Sherpa is the actual. Those are the guys. I'm pretty sure that the Sherpa isn't the animal. Maybe it is. I got this fucking chocolate in my keyboard. Okay. And I lost the cord. Yeah, I know it's not Sherpa, but I can't think of it right now. Yak, of course, it's a yak. Yodeling songs. Oh, internet memes. Interesting. Songs about sleep. Songs about lions. Huh. Why was it a meme? Of course, the lion sleeps tonight. It's got to be Starbucks. No idea. Golden Horde. Oh, this is isn't this just anonymous? Yeah. But this is Slenderman? Ooh. That makes sense. 1991, though. Antisocial. Prisoners of war. I mean, this would be hilarious. I don't think it is, but yeah, never even heard of this guy. Portuguese. No idea. Never heard of them. Skyscrapers in London. Yeah, I'm not gonna get it. Shard. Man, rough showing today, huh? Thomas Pynchon. Novels adapted into video games. I'm sure I know this. Gravity's Rainbow. Interesting. Huh. Okay, well, that's it for today. And we'll I'll either try to do this again tomorrow, still with the, now with the multi-head attention, and just still using lists, and then eventually, hopefully, we'll do a tensorized implementation.